Okay, so the last type of reaction that we're going to talk about is probably the most powerful one that we're going to learn about in this chapter, and it's something that's unique to alkynes that we didn't see with alkenes. Okay, so let's look at what that is. First, we got to discuss an important property that leads to this, which is the acidity of a terminal alkene hydrogen, right? So first of all, we know our alkanes, those hydrogens are ridiculously difficult to remove. A pKa of 50 is like infinite. It's just, you're not going to get it off, right? Alkenes are the same way. They have really, really high pKas, meaning that it's really difficult to remove those hydrogens. An alkyne has a pKa, those hydrogens rather. So this is only relevant to terminal alkynes where there's a hydrogen on the other end. The pKa of those hydrogens is around 25, which is still very high. We wouldn't really consider this to be an acid, generally speaking. Nonetheless, there are bases that are commonly available that are strong enough to remove that proton, okay? And I mean, just to stress how much more acidic these alkynes are than alkenes, that's a 19 unit difference in the pKa, which means that it is 10 to the 19 times more strong of an acid, right? Or really, I don't know if you, thinking about an acid in the strictest sense where it donates the proton, yes, I think it should be thought of more as how easy is it to remove that proton, and it's more doable with an alkyne than it is with an alkene or an alkane, where it's basically impossible. So that means that if we have a sufficiently strong base, that strong base can reach over in our normal proton transfer reactions and grab that hydrogen and create this acetylide ion. So again, and this is probably where that acetylene, acetylide terminology is going to come up more and more. Carbon-carbon triple bonds where that carbon has that negative charge, we can refer to that as an acetylide ion. And just to hammer home why that is, it has to do with the fact that that lone pair of electrons, once that hydrogen's removed, that lone pair of electrons will be living in an sp hybridized orbital as opposed to an sp3 or sp2 for an alkane or an alkene respectively. Why is that much better? Well, you can kind of see just by looking at the shape here. sp2 hybridized orbitals have more what they call S character, so they're smaller and held more closely to the nucleus. So that negative charge is then stabilized by the positive charge in that carbon atom's nucleus, okay? As opposed to being really far and spread out, as in the case with like all the way to the other extreme, the sp3 hybridized orbitals. Remember, we had our ARIO rules, and O stood for orbital, right? So the more S character an orbital has, the more acidic it is. And really, what does that mean? The more stable its conjugate base, so the more stable it is holding that charge. Okay, so now let's talk about which bases can do it here. So let's just do some acid-base reactions, remembering back to like chapter 3, I think it was. So first of all, where do our arrows start? That's going to start at our base, which is going to reach over and grab that acidic proton. Okay. And we're going to have the same thing down here, but now we're going to be comparing two different bases here. And remember how we tell which way this equilibrium lies is we look at the pKa of the acid compared to the conjugate acid. Okay? And what did we say back in chapter 3? Which direction do these reactions prefer? They will proceed in favor of the weaker acid, right? So whichever one has the higher pKa. So here, in this top one where we're using this amide ion, right? This is our NH2 minus. This reaction will lie in favor of the products or in favor of that acetylide ion, deprotonating that sp3 hydrogen. Whereas if we used hydroxide, the weaker base is actually going to be on the the weaker acid is actually going to be on the reactant side. So this one will not lie in favor of the products. And in fact, this is a pretty large difference here. Remember we said like 10 was the cutoff for a reversible reaction. This falls just under that. But basically the bottom line is hydroxide would be a really poor choice for deprotonating this acetylide or this acetylene, right? In general, what we're going to see, well, in general, what we're going to see is that all of our oxygen, negatively charged oxygen species are just not strong enough bases. That acetylide ion is stronger than a negatively charged oxygen. So instead, we got to use something like the amide ion. This is the most common one. You could also use this as a hydride. This is commonly found in something like sodium hydride, right? So NaH, where that hydrogen actually has both electrons associated with it. That can also be used to deprotonate an alkyne, a terminal alkyne. So again, if you remember, I had said like the amide ion is going to play kind of a special role in this chapter, and it has everything to do with this right here, where it's a really commonly used base for deprotonating alkynes, right? So again, if we're going to do a reaction mechanism, which you guys should definitely be able to do, it's just a simple acid-base reaction mechanism. We have our amide playing the role of the base. It's going to grab that proton, and that pair of electrons is going to come and jump onto this carbon, forming that negatively charged ion. I guess the correct name for these is the alkynide ion. I always just call them acetylide ions. I think that technically there has to be a hydrogen here for it to be acetylide. I'm going to be messy like that. Okay, so now what's the big shtick, right? So, okay, great. You can deprotonate that terminal alkyne, a terminal alkyne. Well, the real reason why this is crazy, crazy important is because this acetylide ion or alkynide ion are good nucleophiles. They are strong nucleophiles. And what do we know about strong nucleophiles? We can react them with alkyl halides in order to form a new substitution, right? So we can undergo these substitution mechanisms and replace that halogen with this nucleophilic group. Why is that so special? Because that means that we have just formed a new carbon-carbon bond. Never in any of the reactions that we've studied have we been able to form carbon-carbon bonds. So this is our first reaction where we're forming new carbon-carbon bonds. We actually have a way to grow our carbon backbone in a molecule, which we haven't really had before. So that's why these reactions are incredibly, incredibly powerful, right? They're going to be really useful from a synthetic point of view. And this, again, is just an SN2 reaction, right? So if you replace this with generic nucleophile reacting with alkene or alkyl halide, that's all that's really happening here. It's just now we have this new nucleophile we haven't talked about before, and it is this acetylide ion, or yeah. And again, not only is it a good nucleophile, actually let's use the word strong because that's what we used before, it's also a strong base. So if you remember back in chapter 7, you had these categories of weak nucleophile, weak base, strong nucleophile, weak base, strong nucleophile, strong base, weak nucleophile, strong base, etc. We can update that list to include these types of ions here, which are both strong nucleophiles and strong bases. Okay, so again, this is what we're going to sort of see is this sodium amide, or really the key player here being that amide ion, playing a significant role in these reactions with terminal alkenes. And what they're going to do is deprotonate. And then if we toss in an alkyl halide, we have this way of, again, growing our carbon-carbon backbone. One of the things that is going to get kind of dicey here is keeping track of carbons. It's really easy to add an extra bond or forget a bond. So one of the things that I want you to do is to always double check your carbon backbone. So 1, 2, 3, 4, 5. And remember, there's 2 carbons on either side of that triple bond. For whatever reason, students are prone to forget that. 1, 2, 3, 4, 5. And then we have from our alkyl halide 1, 2, 1, 2. So again, notice that this is our new carbon-carbon double bond, and we actually haven't gotten rid of that alkyne functional group, right? It's still there. We went from being a terminal alkyne to an internal alkyne, but nonetheless, now we can go ahead and we can do hydrogenation reactions, or we could do hydration reactions and create a ketone, et cetera, right? So these are really powerful synthetic tools. If you have, this is the real acetylene where you have 2 hydrogens on either side. These can actually undergo 2 successive halogenations, right? So you can put a halogen on one side and then do it again and put another halogen on the other side. Yes, I forgot to color code these. Okay, and actually these have to be done stepwise or in successive steps. And that's because first you have to create the acetylide ion and then you add your alkyl halide. You can't add sodium amide and an alkyl halide together along with your alkyne. There's going to be a lot of side reactions that take place between the amide ion and the alkyl halide. Okay, so that kind of might sound like a pain in the butt, but it actually turns out to be pretty powerful because that means that we can put different alkyl groups on either side, right? So first I wanted to add an ethyl group to one side, and then in a next successive reaction, I wanted to add a methyl group to the other side. I can do it that way, okay? And then just to go back, all the way back to the very beginning when we were talking about preparation of the alkynes, notice that if we use a compound like this, this is again our dihalide, but it's sort of like, I guess a terminal dihalide. I don't know if that would necessarily be correct, but basically it's on the end, and there's a hydrogen attached to that carbon. Now add sodium amide, not only will we get the formation of our alkyne, but it will continue one step further and we'll actually get that alkynide or acetylide ion, right? It will then so it's a strong enough base where it's going to remove this hydrogen, and that's how I'm going to get my alkyne. But it's also a strong enough base, it's super duper strong, and I can remove this terminal proton as well, okay? So that's why if we wanted to stop at that alkyne step, we'd have to add H2O, which would serve to protonate that terminal alkyne and allow us to kind of stop there. Okay, so just to summarize here, we have these, this is really these 2 different reactions that we learned. First was proton transfer of that terminal alkyne, and then substitution, right? So yes, you should know the mechanism for both of these. This one was covered in chapter 3, and this one was covered in chapter 7, right? So we've done proton acid-base reactions, we've done substitution reactions. These are mechanisms that you should just already know. Regioselectivity. Not in the strictest sense of regioselectivity, meaning which constitutional isomer is preferred. But again, I guess we could throw into this bin that yes, it does have to be a terminal alkyne or there's no proton to donate. And then when it comes to substitution, when it comes to this step here, we'll see, right, primary alkyl halides will prefer substitution. as secondary and tertiary. This will actually be a mixture of elimination and this we will just see elimination, right? So these are just concerns going back to chapter 7, considering that this is strong nucleophile, strong base. And last, for stereoselectivity, there's no such stereoselectivity in the acid-base portion of the reaction. Here, it's an SN2, right? Because it's a strong, or E2. So there are stereochemical considerations. Remember, with SN2, you have that inversion of your stereochemistry. If it's E2, then you have those special considerations. If you only have one beta hydrogen, then your alkyl group, or I'm sorry, your halogen and your hydrogen have to be coplanar. I would review stereoselectivity for those types of reactions. But importantly, these aren't addition reactions that we're talking about. So they kind of fall into previous categories that have already been discussed. Again, the real takeaway here, the real like major 5-alarm fire takeaway here is we have a way of forming new carbon-carbon bonds.